Good evening, viewers, and welcome to this evening session of the topic hypothesis testing. This is a topic which is covered in your economics course of EEC 13, the course on elementary statistical methods and techniques, and it is also covered in your MA Part 1 course of MEC 003 on quantitative methods. This topic on hypothesis testing is one of the very important components of statistical inference. The topic of statistical inference has got two components. One is the estimation part and the other is the hypothesis testing. We are aware that in all our experiments we will be collecting data on the basis of the random sampling technique, and our objective in drawing a sample is to study some population characteristic. We will not be able to study the population directly, either because the census method which we will have to adopt for doing that is very costly, or it is more time consuming, and we also know that by resorting to the technique of random sampling survey technique, we can get reliable estimates of the population characteristic even by the sampling method. Now, what is our underlying objective? Our underlying objective is to study some characteristic on the population, which we call as parameters. And generally we know that average or mean and standard deviation are two important parameters of any distribution. We also know from the study of our earlier units in this course that we have reasons to believe that our sample is drawn from what we call as a normal population, and that population, the distribution of which is containing two parameters by way of mu and sigma, each of which stands for its mean and standard deviation, is going to be our subject of interest, which we are going to study based on a sample. Now, we also know that from the central limit theorem we have the result that if we have n random variables, the sum of those variables are also distributed or together distributed as normal if our n or sample size is large. If n is not large enough, then we also know that we have an exact distribution in T. So this is the basic background with which we will now come to understanding the concepts that we use under this hypothesis testing. We will now begin by trying to understand what exactly we mean by hypothesis. A hypothesis is a statement of assertion or claim, and it is about a population parameter. Let me take an example that we are interested in studying about the per capita income of a district. Now, as I said earlier, it will be very expensive for us to go for a census survey of all the households and the members in those households in the district. For this reason, we will try to make the estimate based on a sample, and we know that by random sampling method we can get valid estimates of the population characteristic, which in our case is the per capita income. So, by this method, we will first of all conduct the sample survey, draw a sample and conduct a survey of those sampling units to get an estimate of our population characteristic, and then we will proceed to test for its validity. These are our two objectives. And when we say we test for the validity, we would like to test whether the value that we have obtained from the sample is close to the value in the population. That is the kind of testing that we do. Now, if we have conducted a survey and we have found out that the per capita income is say about 980 rupees, and if we have reasons to believe that it could be close to 1000, which means it is important for us to have an idea of what the population value is also. If these two things are available to us, we may now like to test the hypothesis that the per capita income that we have derived on the basis of the sample, which is 980 rupees, is close to the population value 1000. Whether it is so or not is what we would like to test. We can consider another example. Say we are having the life in hours of a batch of electricity bulbs. Series of bulbs are being produced and a random sample is drawn, and we have calculated the mean hours of its working, and whether we would like to see whether the average life in hours of the electricity bulbs is close to the population value or not. Another example is, say a new drug is being introduced in the market. We would like to test for the efficiency or efficacy of that drug. We will not be able to observe it after applying it on large number of people or the whole lot of our population, and we would like to do it based on a sample of administration, and we would like to see whether the efficacy of the drug is reliable or not. It is these kind of examples that we will try to study. So when we test the hypothesis, we will be interested in answering questions like whether the sample that we have studied is drawn from normal population. This is in the case of one value if we have calculated. Suppose we have two samples, and from both the samples we have calculated the average. Then we may be interested in testing whether the average from the two samples are equal or whether they are different. That is, one is less than the other or one is greater than the other. This kind of thing we may be interested in studying. So what we essentially mean by this is, if we are to say that there is no difference, we would mean that whatever variation we are seeing, it is attributable to sampling variations. It is attributable to what we call as chance factors. If we are able to do that, then we have been able to decide on the particular aspect that we are trying to focus upon. Having said this, let me now come to introducing some of the very specific concepts which we need to be using while discussing the subject of hypothesis testing. I said that we will have to formulate a hypothesis, and there will be one hypothesis which we call as the null hypothesis, which will be tested against an alternative hypothesis. Null hypothesis is usually stated, we test the null hypothesis for possible rejection under the assumption that it is true. That means prima facie, when we formulate our null hypothesis, we have no reason to believe that it is not valid, it is not true. We will assume that it is true and we will test the null hypothesis for its possible rejection. This null hypothesis is denoted either by H0 or simply by H. Let me say one example, that suppose we are interested in studying the female literacy of a district. Say the district authorities claim that the female literacy in the district is 75%. Now by 75% it means it is 0.75. So we will state in our null hypothesis, say the literacy is denoted by a parameter mu. Our H0 will be mu is equal to 0.75. Now we can test this against the alternative hypothesis that it is not equal to 0.75. We can also test it either for its less than 0.75 value or greater than 0.75 value. Now the alternative hypothesis we will denote again by H1 or A. Now depending on how we are going to state the alternative hypothesis, we will either be able to designate the test as a single tail test or a double tail test. In our, they say this average literacy case, literacy example that I just mentioned, our mu is equal to 0.75 is the null hypothesis. If we are going to state the alternative hypothesis as mu not equal to 0.75, that will become a two-tailed test for us, because our alternative hypothesis will include both the cases of mu less than 0.75 as also mu greater than 0.75. Suppose we are interested in testing the alternative hypothesis that mu is only less than 0.75 or mu is greater than 0.75. In such a situation, our test will be called as a one-tailed test or a single-tailed test. Depending on how we are going to formulate our alternative hypothesis, it will be important for us to select a next concept which I am going to call as which is called as the critical region. And what is going to be our critical region, we will be able to decide based on how we are going to formulate our alternative hypothesis. Now, when we are proceeding to conduct the test, first of all, we should be able to select an appropriate test statistic. What is a statistic? Statistic is a function of sample observations. We have a sample, and based on that sample, from that sample, we should be able to calculate the value of that statistic. Once we have calculated, as I said earlier, we assume that our sample is drawn from a certain normal population, and we know that we are having standard tabulated values for the normal distribution, both for both the tails, that is two-tail test, as well as the single tail, and it is also a symmetric distribution. We know that the one side is a exact replica of the other side. These things we will see very shortly. I will show you the graph of that normal distribution also. So depending on that, we now have the value of the test statistic computed from our sample observations, and we have what should notionally be its true value or its tabulated value, and by comparing the two, we will be able to judge about the rejection or not rejection of our hypothesis. Let me also tell you at this stage, normally we are going to talk in terms of either rejecting or not rejecting the null hypothesis. Although not rejection is same as accepting, the word that is used is for the null hypothesis, either it is rejection or not rejection. So now there is a region of rejection. This region of rejection is based on the sampling distribution of the test statistic. In other words, the total sample space is divided now into two regions. One is the rejection region or the critical region, and another is the acceptance region. Obviously, we can say that the critical region, that is the value, the probability of our test statistic value falls in the critical region, should be small. It cannot be big. This is obviously one thing which should come to your mind straight away, and this is also going to tell us what is the probability of rejecting our null hypothesis H0 when if the test statistic value falls within that critical region. That way this value is going to give us a threshold level beyond which we will not be able to tolerate or have our yardstick as a standard yardstick. Now we know well that in such a procedure we always stand to commit certain errors. There are two types of errors. It is possible that we reject the null hypothesis H0 when in fact it is true. This kind of an error is called as type 1 error, and it is denoted by the Greek letter alpha. Alternatively, we may proceed to accept the hypothesis H0, that is not reject H0, when the alternative hypothesis is true. Such an error is termed as type 2 error. So, in notational terms, this alpha and beta, that is type 1 and type 2 error, is also referred to as the producer's risk and the consumer's risk. Alpha is called as the producer's risk in the sense that there is a chance that he may reject a good lot by mistake. Secondly, that beta, which we call as the consumer's risk, there is always a chance that a consumer may accept a bad lot by mistake. Both of them are mistakes, and errors as we call it, and in our testing of hypothesis we have reasons to control for both these. Can we do it? That's what we are going to say. Now I must tell you that the type 1 error is viewed as more serious than the type 2 error. Why so? To understand this, let us take a court-based analogy which is usually given to bring home this point. We never want to convict an innocent person. We may allow a person who is a guilty person to be acquitted, but we would not under any circumstances like to convict an innocent person. So if convicting an innocent person is termed as type 1 error and acquitting a guilty person is termed as type 2 error, between the two we would like never to commit the type 1 error. Of course our interest is in controlling both, but the normal movement of both these is such that any effort that is made to control one is automatically result in increasing the other. It's not possible for us to control both simultaneously. That is why what we are going to do is we try to set a minimum value for committing the type 1 error. That is also called in our terminology as the level of significance. Usually this level of significance is curtailed, is fixed either at the level of 1% or at the level of 5%. Now having done this, we would like to select such a statistic which is also going to keep our type 2 error, that is beta, also minimum. We know that we want that beta should be minimum is same as to say that we would like to maximize 1 minus beta. This 1 minus beta in our terminology is going to be called as the power of the test statistic or power of the function. Now I have already said that our objective is to control for both, but because we cannot do it simultaneously, we set this alpha at a minimum level. Now this presetting is always done before collecting the sample. This is a very important aspect which should be remembered. You may also recall from your study of statistical inference that this prefixation of alpha or the level of significance is also needed for determination of our sample size. Before the survey, before actually collecting the sample observations, this is determined, and based on this level of significance, a low level of alpha, we will then be able to decide what should be our sample size also. That will take us to a different area, but we will at the moment confine ourselves to our discussion of the issues related to hypothesis testing. Now let me also now introduce to you another concept which we call as confidence interval or confidence coefficient. Now the confidence interval of a population parameter is such an interval where we would like to say, instead of giving one value for our parameter, we will give an interval, and we will say with a high degree of confidence that in 95% of our repeated drawing of sampling and testing, we will be sure to say that our sample value lies, sample value lies within this population value lies within the confidence interval. That is the way in which we will be able to do it also. Now there is also the concept of what we call as sufficiency. If the sample is able to capture all that is to be captured on the population in a complete manner, then we say that such a statistic is sufficient for that particular population characteristic. You will be able to recall that sample mean is sufficient for the population mean, and sample standard deviation is sufficient for the population standard deviation. And in certain cases there will be joint sufficiency also. The sample mean and the sample standard deviation will be jointly sufficient for the population mean and the population standard deviation. Now before we go further, let me also say that if our hypothesis is in terms of parameters, as I said in my early example, I selected mu as my parameter and I stated my null hypothesis as mu is equal to something and tested it against the alternative of mu not equal to something or mu less than or greater than equal to something. If our hypothesis is stated in parameter terms, we call such tests as parametric tests. In such cases, we assume something about our parent population, that the distribution from which the sample is drawn, the sample that it belongs to a certain population is known. We assume that the distribution is known. In other words, we are assuming that our parametric test is a distribution based test. There are situations where such kind of assumptions we will not be able to make, and in such situations we will have to consider non-parametric tests. Non-parametric tests as such is not included in your course, but you have been given one unit in your EEC 15 course, EEC 13 course. Chi-square test, as you would have known, is also used for testing nominal data, for applying it to the nominal data. In such cases, when we say that there is goodness of fit or there is homogeneity of variables, it is possible to say attribute the characteristic to a particular aspect. In such cases, we are stating the hypothesis in descriptive terms. For such applications, we will have to resort to what we call as the non-parametric tests. Now, with this brief description, let me now take you to a world where we will be using many mathematical notations, and I will be showing you the different test statistics, the particular test statistics which will be applicable in our cases, and I will be then also showing you some 2 or 3 practical illustrations based on which you will be able to understand how we are going to test the hypothesis. Let's take quickly a look. Let us begin by taking a look at the normal distribution. So this normal distribution, slide please, as I said, is a symmetric distribution, and if you are able to see this on the screen, it is having the mean at the central mu, and the deviation is this one is it. Okay. So this is having a standard deviation of 1, and if you are able to see it, the distribution function, probability density function, is given by 1 upon sigma root 2 pi e to the power minus x minus mu whole square divided by 2 sigma. So as I said earlier, mu is the mean and sigma is the standard deviation, and this is how a normal distribution looks like. Now, our assumption about the population is that our random variable x is normally distributed, and from that we are going to be selecting a sample for studying the population, some population characteristic. If that were to be the case, we also know from distribution theory that another random variable which we can define as z, in which we will subtract the mean mu and divide it by the standard deviation, that is x minus mu by sigma, is distributed as normal with 0 mean and 1 standard deviation, 1 variance. Square root of variance is the standard deviation. And also we know that if we square this random variable, the z, that is z square, it yields us another distribution which we call as the chi-square distribution with 1 degrees of freedom. Now let us say that we have drawn a sample of size n, small a, from a normal population having mean mu and variance sigma square. Now mean, or the x bar, which we denote it as with one dash written on the x, it will be also normally distributed with mean mu and variance sigma square by n. The standard error will be sigma divided by root n. Now if we add all the variables, I said earlier that one variable from which we subtract its mean and divide by the standard deviation is distributed as a chi-square distribution with 1 degrees of freedom. Now if I am going to sum up all those n variables and square it, the squares of the sum of all those variables, which in the slide I am showing it as sigma I is equal to 1 to n, xi minus mu I divided by sigma I whole square. This is also now distributed as another chi-square variable with n degrees of freedom. I am saying all these things because in our hypothesis testing it will be useful to us, and you will shortly see how they are useful to us. Let me now define. Let me take now two chi-square variables, one x which is distributed as chi-square with n1 degrees of freedom, another distributed as chi-square with n2 degrees of freedom. Let me and the two are independent. This is another property which I require. If that is so, then f, which I will define as x upon n1 divided by y upon n2, this is distributed as f distribution with n1 and n2 degrees of freedom. There are situations where these test procedures will be useful for us, and we will shortly see them. Now let me take a particular case in which I am proceeding to test the hypothesis about the mean of the population, and on the basis of a sample I am going to be testing it. I draw a random sample of size n, and I assume that both the parameters mu and sigma are known to me. I have some reasons to believe that the mu and sigma are going to be roughly around this much. From past data or past experience I know it. If it is so, based on a single sample, I may now be interested in testing the hypothesis that my sample mean is equal to the population mean, say some value mu naught. Now the test statistic z within modulus x bar minus mu naught divided by sigma by root n, I am subtracting the mean, and under null hypothesis it is equal to mu naught. That's why I am taking it as mu naught, and I am dividing it by the standard error, that is sigma divided by root n. This is a standard normal variable. Now if I am having a large sample of size n greater than 30, then I can use this normal distribution, and if not, for n less than 30, this same quantity z renamed as t, say, it is distributed as a t distribution with n minus 1 degrees of freedom. This we will be able to use. We will see how. And suppose there is another situation where we do not know what is the standard deviation. In fact, we do not know even the mean also. So how to say that we can say we know the standard deviation? It is just not possible. So in such a situation, the formula or the test statistic that we will use will be modified by a very small thing, that population standard deviation sigma will be replaced by the sample standard deviation s, and rest of the things will remain the same. And s we are going to calculate by the expression 1 upon n minus 1 summation 1 to n xi minus x bar whole square. This sigma quantity gets simplified as summation xi square minus nx bar square, that is for computational purposes, which you will be knowing, and we will be just modifying the statistic by replacing that sigma by s, and rest of the things will remain the same. Now suppose we are having two samples, and in this case let us begin by taking the first case as we considered earlier, that our population variance is known. In such a situation, we may now be interested, we may have two sample means, and we may like to test our null hypothesis that mu1 is equal to mu2, that our samples are drawn from two normal population having means mu1 and mu2. Once again, here we will now consider the difference of the two sample means x1 bar minus x2 bar, and in the denominator we will be having the expression square root of sigma 1 square by n1 plus sigma 2 square by n2. So this again z, if we call it, is distributed as a standard normal variable with 0 mean and variance 1, and this will be the case for sample size large, which we say as n greater than 30, and otherwise it will be following a similar t distribution with n1 plus n2 minus 2 degrees of freedom. Let's take another situation where we need not even say that our mu1 is equal to mu2. It can be some quantity, mu1, the difference of the two means may be a quantity, say xi, and in such a situation we will be now, we will not, that mu1 minus mu2 quantity, which was 0 and therefore did not appear after the expression x1 bar minus x2 bar in the previous statistic that I displayed, will now get replaced with this xi quantity. So rest of the things will remain the same. This expression modulus of x1 bar minus x2 bar minus xi divided by the square root of sigma 1 square by n1 plus sigma 2 square by n2 is a standard normal variable, and this will be the case if our sample size is large enough. If otherwise, it will be distributed as t, as I said before, with n1 plus n2 minus 2 degrees of freedom. And as I said earlier, as I did earlier in the case of single population, if I do not know the population variance, I will be replacing in the same expression in place of sigma 1 and sigma 2 the quantities S1 and S2, and as I did in the case of single population, I will be estimating the two sample variances by the formula, same formula as I showed for S square. It is 1 upon n1 minus 1 summation 1 to n1 x1 minus x1 bar whole square, and S2 square is 1 upon n2 minus 1 summation 1 to n2 x2 minus x2 bar whole square. Now let me consider another situation in which I draw a single sample, but the observations are paired x comma y, and I have mu I and sigma I is equal to 1 2 as the means and the standard deviations in the two samples, and there is also a population correlation coefficient rho, and let me assume that none of these are known to me, all are unknown. In this situation, we can define a variable z as the difference of x and y, x minus y, and our mean of this variable z will be the mean of the variable x minus the mean of the variable y, that is mu x minus mu y, and my sigma z square, that is the variance of the variable z, will also be having the intraclass coefficient term, that is correlation coefficient term, sigma x square plus sigma y square minus 2 rho sigma x sigma y. Now in this situation, I may be interested in testing for the difference of the two means, that is my null hypothesis will be mu x minus mu y is equal to xi naught, say some quantity xi naught. Now the test statistic t, which is equal to root n z multiplied by z bar minus mu z divided by sz, and now mu z in the next equation I have equated it with the same expression where I am replacing mu z by xi naught, because under my null hypothesis mu x minus mu y, which is mu z, is nothing but equal to xi naught, and that expression I will substitute it, and this is now having t distribution with n minus 1 degrees of freedom, and as usual my sz square will be on the variable z with the similar expression 1 upon n minus 1 summation 1 to n zi minus z bar whole square. Let me consider another hypothesis. I may be interested in testing for the ratio of the two population means, that is mu x upon mu y, which I can call as some expression eta. This, now if I want to test this, my test statistic t defined as root n into z bar minus sz is distributed as t with n minus 1 degrees of freedom. These tests which I am now presently talking of is covered in your MEC 003 course. It is not there in your EC 1T course, but application point of view the same results can be extended, and this is the statistic which will help us to test for the ratio of the two population means. And if we want to test that the population correlation coefficient is equal to some quantity rho naught, say, which is not equal to 0, then the expression t equal to root of n minus 2 r upon square root of 1 minus r square is distributed as a variable t, that is t, a random variable, that is distribution t with n minus 2 degrees of freedom. Now these are, so far I have described some of the applications of t distribution, and now we will see under what circumstances we will be using the distributions of chi-square and then f also. Now let me say that there is a single sample in which both the parameters mu and sigma are known to me, and I am proceeding to test the hypothesis on the population standard deviation. So far all my hypotheses were on the population mean. Either they are same, or the difference of 2 is something, or the ratio of 2 is something. These are the kind of hypothesis that I had been testing on the population mean. Now if I want to test the hypothesis H naught, sigma is equal to sigma naught, some quantity sigma naught, from the earlier slides I showed, you will recall that the square of the random variable xi, I have n sample, and from each I will subtract the mean and divide it by the standard deviation, which in my hypothetical terms, hypothesis null hypothesis, I have set that sigma is equal to some sigma naught. So using that quantity which I know, if I divide it and square it and sum all the variables, this is now distributed as chi-square with n minus 1 degrees of freedom. So this distribution will be helpful to me, this result will be helpful to me for testing the hypothesis that the population standard deviation sigma is some value sigma naught. Now if the population standard deviation sigma is not known to me, then all that I do is I will replace, this is going to yield me a slightly different statistic altogether. Under the null hypothesis, I am setting sigma as equal to some sigma naught, and n minus 1 divided by sigma naught square, which is a constant, multiplied by this s square, which is my statistic. The entire thing is statistic, but s square is the one which I am going to compute by taking the sample values that I have collected. N minus 1 by sigma naught square into s square is distributed as a chi-square variable with n minus 1 degrees of freedom. And as I said in one of my earlier slides, my s square is going to be calculated by the same formula, that is 1 upon n minus 1 into summation 1 to n xi minus x bar whole square. So that is one application of chi-square. But now suppose I shift my attention to testing a hypothesis on the sigma. Now I come to some of the usages of the other distribution f. Let me see. Suppose I have two samples and both mu I and sigma I are known to me. And let me now proceed to set the test the hypothesis that the ratio of the two standard deviations sigma 1 by sigma 2 in the population is equal to some notional value, some constant xi naught. Now f defined as the ratio of the two chi-square variables. This is available to us from one of the earlier results I have already shown. It is chi1 square by n1, first variable, chi-square divided by its standard deviation, its sample size, and the ratio of that to the second variable divided by its sample size n2 is distributed as n1 and n2 is distributed as f distributed with n1 and n2 degrees of freedom. And I can compute the two, since I know both mu1 and mu2. I can have sigma x1i minus mu1 whole square divided by sigma 1 square. All these things are known, and if they are not known, I will be replacing them with the value, with their sample value, but there will be slight difference. Let us see this thing. If I am having two samples and all the parameters mu I and sigma I equals 1, 2 are unknown to me, and I proceed to test the hypothesis sigma 1 by sigma 2 is equal to some notional value psi 0. Now f is s1 square by s2 square multiplied by 1 upon this quantity xi naught square. Now this is distributed as f with n1 minus 1 and n2 minus 1 degrees of freedom. Now having said this, let me now take up some 3 examples which are already given in your course material EEC 13, but I have a particular reason to present it here. Now let us say that there is a case in which the average lifespan of a certain population, which was earlier 60 years, after a certain welfare measure is introduced in the district, we would like to test that hypothesis that H0 mu is equal to 60 with the alternative hypothesis that it is greater than 60. And let me say that my sample size is 25 only, X bar is 60.5, my sample is telling that it is 60.5, and I know I am given that standard deviation is 2 years. In such a situation, if you compute the test statistic X bar minus mu 60.5 minus 60 divided by, that is sigma 2 upon the sample size square root of 25, this yields me the value 1.25. This is my observed value of t. Now for n minus 1, that is 25 minus 1, 24 degrees of freedom, if you see what is the one tail value of the t distribution at 5% level, you can check that it is 2.06. Now since this is higher, my computed value, since that is lower than this table value, we will not be rejecting the null hypothesis, and we will be concluding that the district has not experienced any change in the life expectancy following the welfare measure introduced in the district. This is the way we will be in a position to compare the two values, that is the observed value with the table value, and come to the conclusion on the hypothesis. Let me now take a second example in which I have two sample means calculated, and both the sample means refer to the scores of the students in a test administered in two separate sections, and the average mark scored is 78 and 75, and my sample sizes are 25 and 20. The two standard deviations, I know that they are 4 and 5. Now if I substitute it in the test statistic and calculate the observed value of t, it comes as equal to 2.18. Now for t, from t distribution table, if I now take the two tail value of for 43 degrees of freedom, it is 2.69. Now once again, as I showed in the previous example, I will not be rejecting the null hypothesis, and I will be concluding that the mean scores of the students in the two sections are not statistically different. Let me just take another example in which two samples are drawn from two normal populations, and I am again proceeding to test whether the two sample means are the same, for which I will compute this test statistic, and I get the observed value as 3.3. And since my n1 plus n2 is 20 plus 15, 35, n1 plus n2 minus 2 for 33 degrees of freedom, I verify that for the one tail test the table value is 2.00, and since the observed value is higher, I will be rejecting the null hypothesis, and I will be concluding that the alternative hypothesis of mu1 less than mu2 is in fact the correct thing. So in this particular session, what we have discussed is, we began by understanding under what situations we will be interested in hypothesis testing, how after estimating the value of a population characteristic based on a sample of some size n or a pair of samples as it may be that we draw, how we can proceed to test whether the difference in the means or the ratio of means or the ratio of standard deviations is equal to some population value that we know or we do not know, and how the three distributions of t, chi-square and f are applicable in these different situations, and we have tried to understand how in some given situations we will be able to test the hypothesis that we want to test and come to a certain conclusion on whether we can accept the hypothesis or reject the hypothesis. We hope that this session has been useful to you. If you have any queries, our email IDs are given to you in the course materials. You will be welcome to approach us with any clarifications that you want to seek, and we will get back to you. We will reply to you as soon as we can, either the same day or within a day or two. And we will be covering some of the other things in one of our later sessions, the power of the test and the confidence limits derivative which I introduced in the conceptual part, which I have not been able to demonstrate in terms of exercises. We will be taking it up in our next session. Thank you.